So this is a video about using x11 forwarding on Linux to display Linux windows that are running on a remote server on a local Windows desktop. And the intention is that I'm going to describe how this works with a Windows desktop, and most of the same principles should apply regardless of what your local operating system is. You just have to set up the local side of things slightly differently. So first of all, what is the X window system? So this is something that basically all Linux distributions use to render GUI windows. It's a windowing system that is sort of designed from the ground up to allow you to send not just, if you want to have remote viewing of some GUI applications, you can send not just screenshots of what's on your screen, but in fact rendering commands to be executed on a remote host for sort of more efficient remote access to GUI applications running on a server from your local workstation. So that's what the X window system is. And the idea is there's an X server that's going to actually perform the rendering, and then there's an X client which sends rendering commands to the server. So if you want to show stuff that's running on a remote machine on your local machine, what you have to do is run an X server on your local machine, and then on the remote machine, you have to configure SSH to forward any x11 drawing commands to the X server running on your local machine. So I'm going to show how to do that really quickly now in Putty. So the way you do this is you open up Putty and try to connect to some server. So in this case, I'll connect to the server called Jax. And on the left pane here, once I've loaded these settings, you can see under the connection tree, the SSH branch of that tree, the x11 spot here, you can click to enable x11 forwarding. And I don't actually have to specify a display location here, because just enabling x11 forwarding causes Putty to pass on the sort of appropriate default X display location, at least if you've installed an X server that I'll mention for Windows called xming locally. So if I just enable x11 forwarding and then click open, a Putty window opens. Let me shrink this down so it fits in my recording window, and I can sort of confirm that Putty has sent along the appropriate information by checking the contents of the all caps display variable. And you'll see that the display variable here is going to be localhost 12.0. This is like an address provided by Putty to what's running here. And if you don't have the appropriate display settings, you might want to try localhost 0.0, putting that in your bash RC file, in your bash, home directory /.bash RC file, or whatever the equivalent is for the shell you're using, like a ZSHRC whatever file. You can add the command export display equals localhost : whatever, and 0.0 is a typical default. You'll have to check whatever your X server is expecting. Okay, so assuming that our SSH client is actually passing along the appropriate display host information, we can proceed on with the rest of this tutorial. So once you have that information forward, you actually need to set up an X server on your local machine. So I would recommend on Windows you use xming. It works on machines as old as Windows XP, and it works quite nicely on Windows 10. So this is the site you're looking for, straightrunning.com/xming notes. I think the capitalization is actually required here. Easiest way is just to Google xming and pick out this link. And from this site you can download xming. So xming x64 is probably the one that you want, and or actually you could use the public domain releases down here. I think I typically use these. They're an older version, but they're pretty stable. So I download xming and download xming fonts and install them both, and they have pretty nice detailed explanations on this page of how to do this. So that's installing xming. We're sort of here. That is all finished at about 4.5 minutes in this video. So I'm going to put our X test at 4 minutes and 30 seconds. So this window here, this Putty window, I'm running tmux, by the way, which is why we have multiple panes here showing multiple things. This window was created with x11 forwarding enabled. So if I echo $ all caps display here, you'll see there is some appropriate display forwarding done here, and if I've installed the sort of X utils xeyes and xclock, you can just Google how to install these things. These are a nice way to test that x11 is working. So I can run xeyes, for example. I run this and it's popped up outside of the partially outside the view of my recording here, but I drag it in. Here's xeyes, the program. It's just a silly little program that follows where the eyes follow your mouse. So that works. This is actually running on this remote Linux server. And although it's running on that server, it's displaying locally, and it's not screen piping, it's the actual x11 commands, render commands being forwarded to my xming server, which is running locally, and that's rendering this locally. So the rendering itself is local. That's xeyes. Xclock is an arguably more useful, but still nice and simple test. So it's just a simple analog clock being rendered locally, although the processing is being done remotely. And it's sort of normal to get these kinds of error messages that show up, especially if some fonts are missing. I think on my local system here, I may have actually neglected to install the xming fonts. So some things, this is sort of spotty. Often x11 stuff works somewhat decently. If it doesn't work sometimes, you get what you pay for. You've got, people investing their time to produce these free tools. And when it does work, it can be really fantastic. So I'll show you now sort of a use case where this kind of facility can be super useful. So I'll just edit the text file here as we go, and I'll sort of annotate this with times and so on. Okay, so this use case we're going to cover starting at 6:45 in the video. Okay, so what we're going to look at is a data structure micro-benchmark for sort of complex concurrent data structures. This is a project that my research lab is working on called SetBench. It's a way of benchmarking complex multi-core data structures. So this is a super full-featured software package. We're just going to look at one little slice of this sort of experimental framework called the timeline graph generation component. So if you are using SetBench to evaluate, some concurrent data structures that you're developing, it's nice to know that there are some macro definitions which can help you output really cool-looking debug data, and we can access pictures of that really cool debug data really conveniently by running our experiment on a remote server that's a huge server with lots and lots of cores, and then from that server directly we can process the data and show a graph that shows what's happening, sort of visualizes our debug data using x11 forwarding. So that all happens via several, the rendering of that data happens via several shell scripts and Python scripts, but the generation of the data that we're going to render happens in SetBench. And so we're going to look at timeline graphs where the x-axis represents time from the start of an execution, and the y-axis represents the particular thread that's running. And we're going to draw intervals where some event that we're interested in measuring is actually taking place. So suppose we're interested in measuring this function, add move blocks, and seeing where this function is being executed. And this sort of sounds like something a profiler should show for you, render nice pictures for you. But of course, we can actually measure any arbitrary events we're interested in, not just function calls. But let's think about just rendering this function call for simplicity. So I make a macro invocation to timeline start, passing in a thread ID, which is just something that's passed around often in the test harness, kind of available everywhere. And then once our event has happened, we're to call timeline end, and we're to give a name to this event. This is the rotateEpochBags event. And this timeline end is going to trigger the printing of some time interval measurement for whatever's between the timeline start and timeline end calls. And this measurement is done sort of for each thread that's executing this, each time the thread executes this code between timeline start, and timeline end. So what is the data that's produced by a data structure execution in this test harness with this timeline start and end annotation look like? So I have this file called temp.txt. By the way, this is not Pico. This is an editor called Micro, which is a very nice modern editor. I've just aliased it to Pico because I can't be bothered to learn to stop typing Pico and start typing Micro instead. So I'm going to zoom in this pane so we can see a bit more of this file. And you can see there's some sort of benchmark looking stuff. And then there are all these timeline lines that have some timeline event that we're recording, the ID of the thread that actually executed this particular instance of the event, and the start time and end time as captured by the Intel RDTSC instructions, and a duration in milliseconds of that instruction. And so I can scroll way down here, and here are some rotateEpochBags calls, event sort of reports. And so we'd like to render all of the rotateEpochBags reports that have come out, and there are tons and tons and tons of them. And you might think that this would really color the performance of the execution, so we'd fail to be measuring what we really want to measure and visualizing what we really want to visualize. The fact that I'm outputting all of this data seems like it would really color the performance of a super fast concurrent execution. And it can. And so what I would recommend is, if you're going to do this and print timeline stats in something like gstats, or do something similar, in something like SetBench, and do something similar in your own very different experiments, be sure to run your experiment with and without this capturing and output. Just use, pound sign ifdefs in C or C++ to easily remove and insert all of the necessary calls to print this stuff, and make sure that whatever performance metrics you're measuring don't change between the runs where you actually output this data and the runs where you don't. Okay, so that has to be processed into a format that our Python scripts are expecting, and so that processing is done with this Python script called timeline draw bw.py. Actually, sorry, there's one extra step in here that I haven't shown in this. So there's this script, I have run istbw.sh, single.sh. So this is just an example script that I use to generate this temp file. So I'm just running a command here that has a whole bunch of variables defined, just so they're not sort of buried in this long command. This is a command that's this is part of SetBench. I'm running a command using the SetBench facility. This is the standard way of running a particular data structure benchmark in SetBench. It's a very long command. If I keep sort of scrolling to the right, you can see more and more of the command. This is going to run one particular data structure benchmark. We're grepping some stats from it just to kind of sanity check before we actually do the real work, and then for the particular event type that we're looking for, we do some grepping and cutting and translating to pull the relevant columns out of the file that I just showed you, the temp file, and produce this input timeline BW file, and then we run Python to process that file. So what does the input timeline BW file look like? I'll get out of that, and I'll open input timeline BW. So it looks like this. It's just the thread, 4 columns separated by spaces, thread ID, start time, end time, and duration in milliseconds, filtered down to the event that we're interested in. All the other events are cut out. This is going to be fed to our Python script. It's going to be fed to timeline draw BW. The BW is for black and white. I also have color features. And this is just going to contain some stuff that you set here at the beginning. So you have the maximum possible thread ID. This just has to be an upper bound on the number of threads that you're going to throw at this thing. The window start size ms. This is a useful variable if, so all of the times that you're going to feed to this program, they by default, the times that are output by SetBench by the timeline end are just sort of a number of nanoseconds or cycles from like the beginning of the epoch, the last Linux epoch, so 1970. And so we kind of renormalize all those. We subtract the smallest possible start time from all of the different times that are emitted, and then window start allows you to say, you know what, I actually don't care about the first k milliseconds. So I can cut off, for example, the first 1,000 milliseconds of a run and only view data for collected after the first 1,000 milliseconds by changing that. And window size is I only care about sort of after I've reached that cutoff point, the starting cutoff point, I only care about this much milliseconds. And this is an upper bound. In this case, it's okay to make this an upper bound. If I have a 2-second run, it doesn't show 60 seconds worth of data here. It just shows 2 seconds. And then min duration is we're only going to render events that have at least this duration. This is a way of controlling how many intervals you're drawing on this graph, because drawing, massive graphs with tens of thousands of intervals can just take a really, really long time. So this is a way of kind of filtering that down. And then this is sort of specifying how do I actually pull the relevant data, the thread number, start time, end time of an interval, and the color of an interval from the input data. And this sort of include line function lets you sort of process the line and use the information stored in a line of text in the input file to filter out lines and decide, arbitrary rules that you would like to define to filter out lines of data. So you can change this stuff if you want. The default settings process files of the format that I just showed you. And then this, at the end of sort of configuring this data, it essentially calls timeline plotter, which is defined in timelineplotter.py. And all this does is it loads all of the data from the input file and uses matplotlib to render an image that shows on the x-axis time, the y-axis threads, and then it draws all of the intervals representing the events that you were capturing. Of course, all of the ones that weren't filtered out by all of the criteria specified here in this top file. So let's see what this looks like when we actually run this. We're going to run Python timeline draw bw.py on input timeline bw. So I run this. Okay, so my last recording actually crashed. Super professional setup I have going here. So we're going to just pick up where we left off and try running this script again. So I run this script, and well, we could see it's beginning to draw horizontal lines for all of the intervals. So there are about 5,000 of them that we filtered it down to, so it should almost be done. And here it finishes actually rendering that figure. So now there's a figure for this timeline graph, and it's asking us, do you want to show the figure using x11? I'm just using Python's built-in show function to show the produced image. So normally, if you were working on a remote server like this, what you'd have to do is you'd produce the image, you'd open up your favorite program like WinSCP or something that lets you transfer files back and forth between the server and your local machine, copy the file to your local machine, and then open it. Here, I actually get to open it up directly. And in fact, I'm opening up not the image, but a plot, a matplotlib plot. So I can go yes, open it up, and this is the generated figure showing all of the events across all the threads, at least the ones that we filtered it down to, over a 30-second execution here at the bottom. So 3.0 times 10 to the 10 nanoseconds. And I just want to stress the point. It's really nice being able to open this up and just look at this without having to actually, mediate file transfers between systems and things. And I want to point out, this is actually an intelligent window. This is not a PNG file. This is not an image. This is a plot that I can zoom into. And here, if I zoom into some little plot here, I'm actually going to get zoom on the axes. So I zoom in and you see the axes have actually changed here. I filtered down to smaller threads. I filtered down to a smaller period of time. So it's really nice to be able to just immediately render this and interact with it directly as if you were running it on your local machine, thanks to the magic of x11. So I hope that's interesting and you learned something. Thanks for watching the video.